So this is how far we got with the variational multiscale method so far. We did a decomposition of our functional space or function space H10 into a VH and a V prime. We search for the solution UH in that finite dimensional approximation space. That's going to be our finite element approximation space. And then the fine scale space, all the stuff that is left, was put into this V prime. And well, we carefully looked at what the scale decomposition is all about. And it turns out that there's actually some optimality condition involved already in the decomposition itself via this projector. And then we found a very nice and clean definition of the fine scale space as the kernel of that projector. All the functions in H10 such that the projection is actually equal to 0. And with that scale decomposition, our weak statement also decomposes into, well, two lines for different choices of test functions, denoted here with a star and double star. And then the bilinear form itself also splits into two components in terms of the coarse scales and the fine scales. And then we said, well, this first one, that's going to be our finite element solution because, well, there's only a finite dimensional set of equations here because VH, the test function, there's only a finite number of them. And the solution that we're trying to obtain is our finite element solution. And then we saw here already the fine scale effect onto our finite element solution, which we typically ignore, or maybe not purposely, but that's what tends to happen, or that's what happens if we use a Galerkin approximation. So in this lecture, we're actually going to focus first on the second equation, and that's the fine scale problem. So this one is the fine scale problem. And in this video, and probably also the next one, we're going to talk about how to solve and approximately solve this equation. Our objective is to get an approximation for U prime. But before we start to approximate, I first want to kind of think about what it would take to genuinely solve this problem. So first we're going to try and solve this. Secondly, we're going to try and approximate this. We'll introduce approximations. And third, find or approximate. Well, what are we going to approximate? We're not actually interested in finding U prime, and actually that's already something that you should be aware of. We're not interested in finding U prime. We're interested in finding B U prime, VH. And that's actually a very significant difference because this B is somehow integrals of some operators, maybe differential operators on this VH somehow. Not even sure how I want to write this, but there's somehow an integral involved and this VH involved. And then somehow this U prime also shows in here. And this already illustrates that we're really not interested in U prime, but we're interested somehow in a weighted average of U prime, weighted perhaps by the test functions VH, or maybe weighted by the derivative of the test functions, or maybe weighted averages of the gradients of U prime. Whatever it ends up being, and we'll get to this later, of course, the important thing to realize already is that we are somehow interested in a weighted average, which already kind of we should already realize that's going to be easier than solving for U prime itself, right? If we only need to have its average, then that's going to be a lot easier than trying to find the true function. Okay, but before we get to that, we first want to see what it would take and what kind of conclusions can we draw from trying to solve the true fine scale problem in a complete sense. Okay, so that means that I'm sort of going to rewrite that second equation as an equation for the fine scale solution U prime, and we'll do that under the assumption that we have a given coarse scale, a given UH. So for a given UH, we're going to solve the second equation. And we're going to actually rewrite this into a slightly different form. As find U prime in V prime. And again, this is the kernel of the projector. I think it's important to keep emphasizing that. Such that for all V prime in V prime, we have B U prime comma V prime is equal to L V prime minus B U H comma V prime. And this we will define to be a residual. A residual as a linear form on V. It's linear with respect to V, right? If I double V, then well, both of these are going to double, so the whole right hand side is going to double. So this is a linear form of V. It's not quite linear in terms of UH though, right? If I double UH, then only this one is going to double, but not this one. So I can't say that this is a linear form with respect to UH, but it is a linear form with respect to V prime, and it depends on UH. So that's why I'm introducing this semicolon. So I'm calling this the residual. It is not quite the residual that we're familiar with. The residual that we're familiar with is the strong residual, that is the right-hand side minus the differential operator on the solution. But this is a weak variant of that, and that kind of is based on the fact that B is also a weak representation of the partial differential equation. Right? We don't have a Laplace operator, but we have a gradient UH dotted with the gradient V prime. Now we'll see, however, later on that we can actually move back to the strong residual that we're familiar with. But for now, it's important to realize this is a residual type quantity, but in a weak sense. And it's a linear form with respect to V, and that's kind of what we need to solve this equation. Right? We have a bilinear form, depending on the solution U prime and a test function V prime, and that is going to equal a linear form of a test function V prime. That's already what we have right here. And I think this equation already tells us quite a bit about the behavior of the fine scales, and it's already quite something interesting to think about what this says. This says that the fine scales are somehow driven by the residual of the coarse scales. So if we have zero residual of our coarse scales, well, then naturally our fine scales are also going to be zero. That's what we expect, right? If we have no residual, that means that our finite element approximation can represent the true solution precisely. And more general, this just says that if we have a certain residual, then that's going to act as a force or a source function for the fine scales in pretty much the same way as we normally solve a differential equation where the right-hand side is some sort of force function. Yeah? So the right-hand side here is the residual, and that is driving the fine scales. Okay, I'll give this equation 3 stars. And now our objective is to solve for this equation. And what we want is to obtain a relation for our fine scales for a given coarse scale. And in the end, that's what we'll substitute into that remaining term here that we're trying to treat. So that means that we're now starting to talk about actually trying to solve partial differential equations, something that I have not really addressed yet in this entire class, right? Well, I always kind of stop at the point that we actually have to solve something. We would solve it with the finite element method. And I try not to talk too much about the mathematics of solving partial differential equations, but that is precisely what we have to do right now. And the technique that we use to solve these types of PDEs, at least in the variational multiscale idea, is that we use fundamental solutions or Green's function. So I'm going to take a bit of a sidestep here and talk about what that was. If you've taken a class on partial differential equations, then you probably either came across or heard the term fundamental solution or Green's function, and they're very related. So we're going to take a bit of a sidestep. I'm going to talk about fundamental solutions. Or Green's functions. And that's a general strategy for trying to solve a partial differential equation. Some arbitrary partial differential operator acting on our field of interest phi, such that that is going to equal some sort of right-hand side, f. And so as a general partial differential equation. And then as long as it's linear, this is going to work as long as this is linear. So the general idea of trying to solve this, well, you have multiple strategies, right? We can try and find a Fourier series or some separation of variables. But a very general idea is that we're going to find the fundamental solution or Green's function corresponding to this problem. And that is going to be the function that satisfies the following partial differential equation. We're going to solve a different partial differential equation. We're going to solve the adjoint differential operator. Get back to that in a second. Acting on a special function, g, for Green's function, which now depends on two fields. Well, x, first of all, but now also a new parameter x hat, such that that's not going to equal f, but that's going to equal the Dirac delta distribution, centered at x hat. So because I'm now going to introduce two variables, let me be very explicit here. F would be a function of x, phi would be a function of x. This distribution, you can think of that as a function of x as well. And these differential operators all also act in terms of x, right? So if we have a derivative, then that's the derivative with respect to x and not with respect to x hat. And I'm going to have to shuffle these variables in a second, so that's why I'm specifically addressing this. So what is this L star? I think we came across this concept before, but I want to specifically address it again. L star is the adjoint operator, or the adjoint differential operator. So that's the specific operator such that this equality holds. W is equal to V L star W. Given a function V with certain boundary conditions, such as that it's 0 on the boundary, and then integrate over the entire boundary. Yeah, so actually specifically this should be true for all test functions in the sense of functions that have 0 values and 0 derivatives on the boundary. So that's a differential operator. You would obtain this from integration by part steps. Just as a kind of a rule of thumb, here we have a couple L's and L star. So the Laplace operator delta, that's simply going to be delta itself. We call that self-adjoint. If you do integration by parts twice, you obtain the Laplace operator on the other operator. But the same is not true for first order operators such as the gradient. Those actually become minus the gradient. Every iteration of an integration by part steps, we have to introduce a minus. As a first order operator becomes one negative, that operator. Second order operator becomes one negative negative, or again just the operator itself. So those are two examples. And also the only two that are going to be relevant for what we're talking about. So suppose that we solve for this particular new iteration of the partial differential equation. And the key idea is that I only have to do this once. Yeah? F might be a very complex function, but this delta is always going to look the same. Well, okay, apart from this parameter that we have a position of delta. Just to make clear that what I'm talking about here. So delta, we typically draw that as an arrow. It's a Dirac delta distribution. The location of this arrow is going to be x hat, and the variable here is just x. So suppose that we have found this function, this Green's function. What I can do then is that I'm going to take my partial differential equation and I'm going to multiply the left and the right side by this function g. And after I've done that, I'm going to integrate over the domain. So what do we get? We have L acting on x of phi, a function of x, multiplied by g x comma x hat, integrated over the domain. It's going to be equal to integration over the domain of f times g x x hat. Yeah, so taking the partial differential equation, multiply both sides by g, integrate over the domain. So naturally, because of this definition of this adjoint operator and what we have on the right side over here, I can rewrite the first term as an integration over the domain of phi, well, function of x, times L star times g x comma x hat. Maybe I should also emphasize what we're integrating over, so we're also integrating over x. And by definition of how we obtained this function g, this is actually going to be equal to the Dirac delta distribution. So we obtain here that the phi times delta x hat, both as functions of x, integrated over x, is going to be equal to that. And that, by definition of the Dirac delta distribution, is going to be phi at x hat, which again is still equal to f g x x hat dx. And also f is a function of x. Okay. So, given our function g, we can find the solution phi at any location by carrying out this convolution integral, this integral of f times g over x. So g is in fact sort of a function that tries to take into account the influence of all the surrounding domain onto that point. And I have some example figures here. So this is the fundamental solution of a, I'm going to get rid of my, try to restart this. Yeah. So this will be the example for the Laplace equation on a disk. And this will be the fundamental solution, or the Green's function. So this is going to satisfy that if we take the Laplace operator, it's going to be equal to the Dirac delta distribution at, in this case, the center. So that means that, well, first of all, it has to be 0 all over the domain, right? So if we take the Laplace operator of this function, then you'll find that it's going to be 0 all the way over the domain, except for precisely at the center, where we get this, this spike. And that's the Dirac delta distribution. And that spike has to then satisfy these properties of the Dirac delta distribution. That if you integrate over it, it actually has an integrand of 1. There's more rigorous definitions of this kind of stuff, but I'm just trying to illustrate the thought process here. So the way that we interpret a figure like this is that at the center location, this is how the solution would depend on the surrounding source functions, right? So if we have a certain source function all the way over here, and then how much is that going to contribute to the value of the function, of the solution function at the center. Okay, so this for a Laplace problem. For a advection-based problem, they're not going to look quite so symmetric. I have here a one-dimensional and two-dimensional example. Our x hat is again at the point of the break or the spike. So if you take the advection diffusion equation or the advection diffusion operator, have it act on this function, then you'll find that this is actually going to be equal to 0 everywhere, except for at that center location you'll get a Dirac delta distribution, and then it's going to be 0 everywhere else again. And same thing for the lower figure here. So again, the way that we interpret this is that this is showing that at this location of half here in the one-dimensional case, how is that solution going to be impacted by the surrounding sources? Well, naturally, upwind is going to have a large impact, whereas downwind, the source function, the body force, is not going to have a lot of impact on the solution at half because, well, it's being transported to the right. Yeah? So everything that we expect to have an influence on our solution at point half is everything that has been contributed to the flow upstream. So that's how we interpret these graphs. Okay. So this function g x hat is what we call the Green's function. And well, this function, what is it about? It's about how is my solution at x hat affected by sources at x. Good, okay, so that was our little side tour here. How are we going to use that? Well, we're going to introduce a concept called the fine scale Green's function. And that's what we're going to try and use to solve, well, the fine scale problem. So the fine scale Green's function solves the following problem. The fine scale Green's function solves the following problem. Find g prime x comma x hat in our fine scale space, again kernel of the projector, such that for all test functions, and I'll introduce a new symbol here, w prime in, well, fine scale space, we have that the bilinear form of w prime comma g prime is going to be equal to, well, simply w prime at x hat. Well, the way that we would write this more cleanly is as a linear form right? This is the same thing, right? W prime at x hat, well, that's precisely this Dirac delta acting on W prime, which is in fact simply some sort of linear form acting on W prime. I'll write the linear form as D for Dirac delta. Now, I don't want to use L because we're using L already in the original statement. Just to emphasize our variables again, okay, this was pretty clear. We're integrating over x, so this is x, and all our integrands in the bilinear form are also integrands on x. Okay, so then this should be relatively straightforward. So what is the relation between this statement and the statement for the Green's function here and our original problem? Well, the statement for the Green's function was this adjoint differential operator producing a Dirac delta. So again, we're producing a Dirac delta here, and adjoint because if we take a look at the original fine scale problem, then we have the test function in the second slot, but now we're putting the test function in the first slot. So that was not by accident. That's actually precisely what makes this the adjoint. You can show this by doing the integration by part steps, then you'll find that these variables flip around. So this is actually the adjoint differential operator, this guy, but then encoded in a weak sense. And because we're dealing with a weak sense, we're testing by test functions, and then the Dirac delta, well, that is precisely the operator that produces, well, the value of the test function at a certain location. Yeah, so this is precisely the standard Green's function strategy, but then in a weak statement, specifically for the fine scale problem, and fine scale problem only because we're choosing to restrain ourselves to these fine scale spaces. Yeah, so in fact, you could probably more rigorously define the notion of fine scale Green's functions also just in a weak sense by doing precisely what we're doing here. I wanted to illustrate it in the strong sense because this is probably what you're familiar with from your partial differential equation classes. Okay, so suppose that we have obtained this function, and again, this would be very difficult to obtain in practice. In some certain cases you can do this by hand, but otherwise you would have to do this with a highly refined finite element mesh, right? Because we're trying to obtain a fine scale effect here. So given that function, we substitute v prime as a function of x is going to be equal to g prime as a function of x and x hat into this equation 3, our fine scale problem, to obtain. So I'm taking equation number 3, the fine scale problem, but then with the residual forcing. And this is an equation that holds for all choices of test functions, right? All choices of test functions v prime in our v prime space. So that means that I can do this well for certain choices, every possible choice, as long as it's a function in v prime. And in fact, the Green's function was precisely defined to be a function in that fine scale space, in this constrained space. So indeed, I can choose, if I want, I can choose v prime to be equal to my Green's function. So what happens if I make that choice? Well, what do we get? We get b u prime as a function of x. Now I'm going to substitute this into here, b prime, u prime, v prime. So that's now g prime, our fine scale Green's function. Well, what's that going to be? Well, by definition of our fine scale Green's function, this was going to equal w prime. Well, for every w prime and every function in v prime, well, by definition, u prime is a function in v prime. So this is going to be equal to u prime at x hat. And again, that's going to be equal to the right-hand side here, but with the fine scale Green's function in place of the v prime. So this is going to be equal to the residual acting as a linear form, the weak residual acting on g prime, where again our residual was also a function or functional of UH. Okay, so now we have an explicit relation that couples our coarse scale function with a fine scale function through, again, the residual in a pretty clean way. We have an explicit relation where in the residual we only have to substitute this special function g prime to obtain our fine scale function for any given coarse scale function. So there's two applications to something like this. We'll see that this is going to inspire our modeling strategy to obtain a fine scale model. But secondly, the thing that I would also like you to think about at this point is that the fine scale solution is really nothing more than the error. If we define UH to be an approximation and we have U is equal to UH plus U prime, then U prime is naturally just the error. I prefer talking about it as the fine scale solution, but in effect it's nothing more than the error. So this also gives you sort of an error estimator. For a given UH, how does the error distribute? Well, that depends on the fine scale Green's function. Now, this is not just a hypothetical concept. We can also compute these fine scale Green's functions. Here again, we have two Green's functions. But if we now perform the same analysis, but now in the fine scale space, so this V prime space, which depends on the projector, then we get other functions. Maybe I should first point this out. The Green's function is a function of two parameters, x and x hat. Here we have x on the x-axis, and x hat is this location of this kink here. So you should actually be drawing the Green's function as a 2D function for a one-dimensional domain. The x-axis itself and then also for every possible location of that kink, and that's here the depth parameter, right? So this plot here would be one slice of this two-dimensional plot along a certain choice of x hat, right? If this is x hat, then you would have to take here this plane as x hat, and then you will indeed find precisely that function. Okay, proceeding with my earlier talk. The fine-scale Green's function, we would do the same thing, but we would try to solve this in the fine-scale space. That gets a little technical. I won't go into the details of how you would actually do that. I just want to give you a feeling for what these functions will look like. And that's going to be something like this. So there's a couple of things that are quite interesting here. First of all, the fine-scale space depends on the projector, right? We define it to be the kernel of the projector. So for different projectors, you will get different fine-scale Green's functions. This is the fine-scale Green's function for the H10 projector, the one that we in the last video concluded to be a very good one. And we concluded it to be a very good one because it gave not the exact solutions in the one-dimensional case. So it produced solutions that were nice. But now we see another property of the H10 projector that is very, very positive. The fine-scale Green's function localizes. This is the fine-scale Green's function on the complete domain from 0 to 1, but for an x hat that is in a certain element, and then the fine-scale Green's function actually localizes to that element. So this fine-scale Green's function is 0 everywhere except for in that element. So that's not something that I forced it to be. That is a result from simply computing the fine-scale Green's function in that fine-scale space, the kernel of the projector. So that 2D graph, if we start to vary this x hat, then we see that it kind of jumps from element to element, and then these are each the element domains here. Yeah, so it always localizes per element. So if we then zoom into one element, those are the graphs at the bottom, and then we see that for the p is equal to 1, so the polynomial order of 1, we actually get the same graph as the one before, this one. So then in the polynomial order of 1 case, our fine-scale Green's function becomes, well, the original Green's function on the whole domain, but then compressed onto a single element. That's what the fine-scale Green's function looks like. For higher order basis functions, we get more complex fine-scale spaces, these v primes, because our projector is able to project on a richer space. It's going to remove certain modes from our collection of fine-scale functions, which means that also our fine-scale Green's function becomes more and more complex. So this is p is equal to 2, and this is p is equal to 3. So those are not very important for what I want to say. All I want to say is that you can solve this and they become more complex. The important thing is really this localization. So this is in 1D. In multidimensional cases, that's not going to be true anymore. We don't get pure element localization. Here I have for two different projectors what the fine-scale Green's function would look like for a particular choice of x hat. So I suppose x hat is right over here. And then we see how the fine-scale Green's function looks like from the top or from the side here. And again, the fine-scale Green's function is defined to be the solution in the fine-scale space. And the fine-scale space dependent on the projector. So here we again see for two different choices of projectors how this fine-scale Green's function what this fine-scale Green's function looks like. And here we again see that this H10 projector is actually the better projector, not only because it produces better solutions, but also because it produces better fine-scale or scale interaction in general, or interaction with the fine scales. And what we see specifically is that it localizes much more than the L2 projector. The L2 projector has a huge spread, whereas the H1 projector has a relatively small spread, and you can already interpret this or think ahead to the fine-scale modeling. It's going to be easier to model something, a scale interaction that is localized versus a scale interaction that is global, right? So think again about what it meant, what a fine-scale Green's function meant. That is, given my solution for the fine scales at this point, how is that affected by all its surrounding? and very explicitly, how is that affected by the surrounding core scale residual? Well, it's either relatively localized in the H10 projector or very widespread in the L2 projector. So this is saying that even 20 elements away from our fine scales, we still have influences from the core scale residual, whereas for the H1 projector, it's relatively localized. Okay, I think that's what I wanted to say. Oh, okay, I have one more slide. So so this is for different choices of projectors. We can take this a little further and also look at different methods. I'm not going to go into too much detail here, but what I want to emphasize, or what I want to say, is that there are certain implicit projectors to different methods. We saw an implicit projector already in the second video on this series, the Galerkin orthogonality projector, that if you take the Galerkin approximation, then you're, without realizing it, making use of a certain projector. And those projectors also have fine-scale Green's functions and scale interaction distributions. So in my own research, I try to explore this context for advanced finite element methods, such as discontinuous Galerkin methods. And then we see quite an interesting result, where on the right graph you see the fine-scale Green's function, or sort of a derived quantity, for the local discontinuous Galerkin method, one of the ones that we also saw in the table on diffuse methods, or diffusive fluxes. And on the left graph you see something that is more of a conformal finite element method. That would be more the standard method. So the left graph is going to be the standard method and the right graph is going to be the discontinuous Galerkin method. And then we see exactly that, pretty much the same thing as the top and the bottom graph here, that we get localized fine scale behavior, localized scale interaction for the discontinuous Galerkin method, and for the standard finite element method we get a widespread behavior. So this was for kappa is equal to 10 to the minus 2. We can push that a little further, 10 to the minus 3, and we get more advection dominance. And then we see that this becomes the difference between the DG method and a standard method becomes more pronounced. And in my own research, I use this as a motivator, a motivation for saying that DG methods are more robust, right? So what does it mean for something to be robust? Well, it's going to work even if we make small mistakes. Well, that's precisely what we're doing. We're making small mistakes. We're not taking into account the fine scale effects in DG methods. And the error that we're introducing, well, is small and localized. Whereas if you don't take into account fine scale effects, if you don't take into account a turbulence model for a standard finite element method, well, then you're making a huge approximation and a huge mistake in that sense. Yeah, so I use this in my own research to explain why a discontinuous Galerkin method is robust versus a continuous Galerkin method, not so much for these hyperbolic problems. Okay, I think that was quite a long video, relatively speaking, but we introduced quite a number of important concepts. The fine scale Green's function, we saw that the fine scales can be interpreted as being forced by the residual of the core scales. Then the fine scale Green's function shows how that residual of the core scales affects the fine scales, and we extend the concept of a Green's function to the fine scale Green's function, where we're trying to solve this in the fine scale space, where we see that different projectors lead to different fine scale Green's functions and scale interaction. Yeah, so the next step is going to be, how do we now approximate this to come up with a practical method, a practical finite element method. And so I'll get to that in the next video. So thank you for your attention.